For multimodal, you have here several points where you have f prime equal to x, and this is also minimum, and this is maximum, and so on. So you can have like this one, local maxa, local minima, and so on. This is a multimodal functions. You have several stationary points, let us say. There is a distinction between the global extremum, which is the biggest or smallest. When we say extremum, yani global minimum or global maximum, between a set of extrema and the local extrema, any extrema. Of course, you can, this concept is very clear. I suppose them, or suppose them. Not many numerical procedures terminate at a local extremum. For classical optimization, for gradient methods, if you are minimizing a function, and if you start here, you will go through and you will be trapped here. But maybe there are some, global optima here, and this is the limitation of the classical techniques, which is not there in evolutionary computation. Evolutionary computation, as we mentioned, it's population-based techniques. It started with several solutions randomly scattered over the search space. So most likely you will not be trapped in local minima. You start with one solution here, one solution here, one solution here, one solution here and there. So you can, eventually you can reach to optimal or near optimal solutions with the evolutionary computation. And this is the advantage of evolutionary computation over the classical techniques. So this function, for example, is multimodal. You have here local maxima, you have here local minima, you have here global maxima here. You have this is a saddle point or a stationary point or inflection point, where you have here a derivative equal to 0, but this is not maxima or minima. You have here the global minima, this point, and so on. So this is a multimodal function. And the slope of fx at the point x in the direction of the ith coordinate axis is, you can, of course, if you have a function, you can get the derivative of the function. Maybe the function is a function of x, or if you have x1, x2, 3, 4 variables here. So you can get partial f by partial x1, and partial f by partial x2, and the partial f by partial x3, and so on. If you have those equal to 0, and you solve, you have 3 equations and 3 unknowns, x1 and x2 and x3. So you can, in principle, you can solve these 3 equations to find x1, x2, x3. So the points where you have the first derivative equal to 0. These are the stationary points. Of these partial derivatives is termed as a gradient vector, denoted by, you have here the gradient of f is the vector containing partial f of partial x, partial f of partial x, 1, 2, 3, 4, and so on. So this is called the gradient vector. As we will see later, these gradient vector, we will equate each entry here equal to 0 in order to get the stationary points. So let us assume this, for example, f of x equal to x1, x2 square plus x2 cosine x1. So this is the function. You have 2 variables here, x1 and x2. So you can get partial f of partial x1, the gradient vector, partial f of partial x2. So this will be, if you take the derivative with respect to x1, so this will be x2 square plus x2 cosine to the sine minus sine x1. So minus sine x1. And this is, of course, the derivative of this 2, the 2x1, x2, and x2, cosine x1 is a constant, and this is x2 is 1, derivative is 1. So these are the gradient vector. Okay. So the stationary points are given by simultaneously solutions of this part equal to 0 and this part equal to 0. So if you solve these two equations, you will get the stationary point. طبعا these are nonlinear equations, and of course you can use any iterative method in order to solve this, like Newton-Raphson method or Gauss-Seidel method or whatever. Usually this is the trivial. If the gradient is constant, معناه ان the function is linear. Function is cx plus alpha. And if the gradient, for example, if the gradient is of the second derivative is constant, then the first derivative is linear, and so on. And the function is quadratic in this case. The second derivative of any variable function is defined as partial derivatives. If you have such function here, this is the first derivative. This is the gradient vector. Can you find the partial square f? Partial square f here will be over partial x1 square. You can get partial square f by partial x1, partial x2, partial square f by partial x1 and partial x3. And you take the derivative. This is the derivative with respect to x1. So we take the derivative of this again with respect to x2 and again with respect to x1. And for this symbol, let us remove this. And we have only two variables here. So can we get this one? How much is this one? Partial square f partial x1 square. How to get it? What we have here is partial f by partial x1. Can you get partial square f by partial x1 square?
Yes.
Another derivative with respect to x1. So what do you think? What is the solution now? Here.
Minus x2 sine cosine x1.
And we take the derivative with respect to x1 again. So this will diminish. And you have here sine x1 will be cosine x1. So minus x2 cosine x1. طيب, can we get partial square f by partial x1 partial x2? This is partial x1. Can you get the derivative with respect to x2 again? So this will be 2x2 minus x2 sine x1. Exactly, minus sine x1. You take the derivative with respect. Again, you can have partial square f by partial x2 square. You take the derivative here with respect to x2. And partial square f by partial x2 partial x1. So you take the derivative with respect to x1 here in this second base. So what you can have here, in the second derivative, you have 4 entries. Now, you have 4 entries, partial square f by partial x1 square, partial square f by partial x1 partial x2, so you end up with the 2 by 2 matrix. This matrix is called Hessian matrix. This is the second derivative here of the function. with multivariable. So this Hessian matrix, of course, plays the same role as d square f by dx square. When you want to get the maximum or minimum value of the function, you get for only one variable. You have df over dx, and you put this equal to 0. And you calculate this one at these values here. So you get x here, and then you substitute in the second derivative, and you see whether the second derivative is positive or negative. If the second derivative is positive, yet this point is what? If d square
Maximum.
f by dx square greater than 0, but this is a
minimum.
local minimum. Local minimum. If it is less than 0, يبقى local maximum. The Hessian matrix plays the same role. But since this is the matrix, so we can get, instead of having this d square f by dx square greater than 0, we can look at the eigenvalues of the Hessian matrix. If the eigenvalues are positive, but this is the minimum value. If the eigenvalues is negative, but this is the maximum value. If the eigenvalue is 0, but this is a flat point or a stationary point. So this is the second derivative. And of course, you can create what we call Hessian matrix. It is n square matrix, n by n, and square symmetric matrix determined as such, h of x equal to this. Okay, so for that example, again, this is the second derivative with respect to x1, x2, x2, x1, and x2 square. So this is the second derivative or the Hessian matrix for that example. Of course, when you solve these two equations here, to get the minimum or the stationary points, when you solve these two equations, to get the stationary points, you can have x1 and x2 and substitute here in the Hessian matrix by x1 and x2 found earlier. And in this case, you have 2 by 2 matrix, so you can check its eigenvalues here. If the Hessian matrix is a constant matrix, لو دي constant matrix, يعني you have Hessian matrix is 2, 0, 0, 1, whatever يعني. In this case, يبقى the gradient is linear and the function itself is quadratic. Okay? Is it clear? It's some kind of integration rather than differentiation. So this is f of x, and this is straightforward. If you have any question, please raise your hand. Abdullah Yusuf.
Doctor,
Yes.
what is if some of the eigenvalues are positive and some of them are negative? What can we say about the function, about the point?
About the point, as we mentioned, if they are strictly positive, if all the eigenvalues are positive at this specific point, and here, this is 2 by 2 matrix, right? And you have from the gradient f, you put it equal to 0 and you solve to get x1 and x2. So you take x1 and x2 and substitute here, so you can get the eigenvalues, lambdas, here. If lambdas are greater than 0, then this point is what? If lambda is greater than 0 or second derivative greater than 0,
This minimum.
Minimum. If lambda greater than less than 0, but this is maximum. If lambda equal to 0, but this is flat point or inflection point. Okay.
But we have more than one eigenvalue. So if one is positive and the other is negative, what can we say?
One is positive and one is negative?
Yes.
This is not the case, Hussein.
Okay.
At a certain point, you either have maximum, minimum, or flat. Let us see some examples, and maybe we share the same point, but I don't think you have such a situation. Okay. One important issue in the optimization, the convex or concave functions or regions or search space. Convex, concave functions. What is the definition of convex and concave? For this one, as you can see here, this function you can see has a maximum value. There is a maximum value here. And this is called concave. Mathematically, we will define the concave, and let us see the opposite. This is the concave function, and this is the convex function. You have a local minima here. So the function is convex. Mathematically, we can express this principle. You can see here for this example, for this function, for example, if you take any 2 points like x1 or xa and xb, it is given here. xa, this point is xa, and this is the function of xa. The value here is a function of xa. And this is xb, and this is the function of xb. Okay? If you take any point, if you interpolate between xa and xb, if you take any point somewhere here, if x, what is the function? What is the value of the function at x? This is the value of the function at x. This is f of x. Okay? Here, as you can see, f of x is greater than any interpolation between f of xa and f of xb. Any interpolation here, you have it here. So the function of x, of the interpolation over x, is the greater than the function of any interpolation between f of xa and f of xb. So this is the definition, or mathematical definition, of the concave. The convex is the opposite. If you take any point here, this is the function of f of x, which is lower than the interpolation between f of xa and f of xb. So the function here is lower than this. So let us describe this mathematically here in this. A function is called the concave over a region R if the interpolation on x, theta is somehow constant between 0 and 1. So if you interpolate over x, the function is greater than interpolation over the function values of f of xa and f of xb. Okay? Is it clear? The definition is clear? Definition is clear?
No.
Okay, so let us go back to this one here. If you want to interpolate between XA and XB, so you will have a value here somewhere in between, right?
Yes.
If you interpolate between f of XA and f of XB, so if this is the line in between, so you have any point here is the interpolation between which is in between f of XA and f of XB. This is the interpolation over the function value of f of XA and f of XB. Am I right?
Yes.
So the function of x, which is the interpolation between XA and XB, the value of the function here is here. This is the value of the function. This is the function. Okay? So the value at x is here. And the value of the interpolation is here. So the value of the function at x is greater than the interpolation between f of XA and f of XB. Is it clear now or not clear yet?
For me, it's clear.
Doctor, we have to take a straight line. We have to take a point on the in the straight line between XA and XB. Right?
I didn't hear you well. So can you?
I'm saying the other point should be a point that lays on the straight line between XA and XB.
Yeah.
I mean, we have to draw a straight line between f of XA and f of XB and take a value on that straight line, right?
Yes.
Okay.
This is the interpolation of what? This is the interpolation between f of XA and f of XB. This line,
Yes.
يعني for example, if f of XA, خلينا نقول f of XA equal to 5, f of XB equal to 4 مثلا, or 3. If you interpolate, you will get a value here between 3 and 5. And for example, if you take مثلا theta equal to 0.3 مثلا, so this equal to 0.3 times 5 plus 0.7 times times 3. 0.3 theta, and this is 1 minus theta. Okay, theta and 1 minus theta. So 0.3 times 5 plus 0.7 1 minus theta times 3. So this becomes 0.15, 1.5 plus 2.1. So this equal to 3.6. So this is the interpolation between f of XA and f of XB. Is it clear?
Yes, now it is clear, Doctor. Thank you.
So now, if you interpolate, if you take any 2 points, any 1 point between XA and XB, وليكن مثلا if this is 1 and this is 3, if you take مثلا 1.5, you will get 1.5 here is f of 1.5, هنقول بقى هنا f of 1.5 هتلاقيها greater than theta, whatever the interpolation factor, of f of A, which is 5, f of XA, plus 1 minus theta multiplied by f of XB. Is it clear? And the opposite is here. So if you interpolate if you choose any value between XA and XB. So وليكن مثلا افترض ان theta is half. So if you take the midpoint between XA and XB, you will find the function of the midpoint here, assuming that in theta equal to 0.5. So this is the midpoint. If you take the midpoint between XA and XB, you will find the function of this midpoint greater than the interpolation of the function of A and the function of B. Is it clear? So in this case, this is the definition of the concave function. And the function is strictly concave if this replaced by greater. Only greater, not greater or equal. So we exclude the equality. We exclude we have strictly this. If you take any 2 points, you will find the function is higher than the interpolation here. Is it clear? And you may have such function. If you have a flat point here, if you take this is x1 and this is x2, you will find any point here, the function is the same as the straight line between the functions of x1 and x2. So in this case, it might be equal here. So if it is only all over the search space, all over the range that you are interested in, and these values, the function value here of the midpoint or interpolated point here is greater, in this case we call it strictly concave. A function is called convex, which is the opposite, or strictly convex if this greater than or equal replaced by less than or equal. So if this is the case here, as we mentioned in the previous slide, you have here the interpolation here is greater than the function itself. So in this case, this function is less than or equal. So this is convex. Strictly convex, you have only less than here. Is it clear? طيب Khalid Sulaiman, please. If you have a question, Khalid.
Yes, Doctor, please. Theta is bound by 0 and 1, and I want to ask you, how would the choice of theta affect the convexity or concavity of the function? How would it affect the choice of theta affect the function?
This is theta. Theta varies from 0 to 1, right? Any value. Theta can take 0, can take 0.1, can take 1, any value between 0 and 1. If this is valid, okay, whatever theta is, in this case we call it concave or convex, depends on whether this is greater than or equal. Greater than or equal, or less than or equal. The convex. Whatever theta is. The number of, if for example, between these points, if this is the case, مثلا, if this is the case, maybe if you interpolate, here is x1, here is x2. If you interpolate, if you are very close to x1, you will find the function is concave. When you have other value of theta, or this interpolated point here, you will find this value, this function here is what? Is concave, is convex, right? Right?
Yes.
Or not?
No,
So
it is right.
the function here is concave. The function here is convex. So you are interested in a certain range. Whatever theta is, if you take theta between 0 and 1, whatever the value, and you found this is valid, the function is concave over this range of x1 and x2, or xa and xp. Okay?
Okay, doctor.
Did you get the point?
Yes, but what is theta arbitrarily chosen?
Yes.
Okay, okay. Now it is very clear.
And any point taken between x1 and x2, and you found this is valid, the function is concave. Any value between x1 and x2. If this is violated at a certain values of theta, يعني theta equal to 0.5 معناها mid point. مش كده ولا ايه؟ مظبوط؟ لو theta equal to 0.5 معناها mid point. If theta is greater than 0.5, يعني you are weighting this value is higher, so you are very close to this one. If theta is greater than less than 0.5, معناها انه you have here, you are weighting this more and more. So whatever theta is here within this range, if this is valid, يبقى the function is concave. Otherwise, we cannot say the function is concave over this range. I mean, in conclusion, theta can take any value between 0 and 1. Okay? طيب خالد سليمان خلاص, did I answer your question?
Yes, yes, very much. Thank you. Thank you.
طيب سالم غانم.
Yes, Professor. So out of this discussion, we can say that power system, especially the power flow equations, are neither convex nor concave, and we cannot resolve it using the classical methods. Is that accurate statement?
Load flow?
Yeah, the power flow equations and power system equations in general, they are not convex.
Are not what?
Are not convex functions. They are not convex, are they?
Usually, what you want to do, actually, these are in load flow. Load flow simply عشان بس other, if your background is not power, load flow equations or whatever, it's f of x, and these are algebraic nonlinear equation. Okay, and you actually in these equations, you're solving them using the Noether-Raphson method or Gauss-Seidel method. You take the derivative here, the derivative partial b, and power by partial theta, partial v, and so on, and you put them equal to 0. So you can get the Jacobian matrix. And so you are searching for the equilibrium point. Okay, and this equilibrium point is minimization problem. لأنك أنت, if you still remember يا سالم, you are minimizing the error.
Yeah.
You are minimizing the mismatch between or the error delta B and delta Q. So you need to, this is your objective, is to minimize the mismatch between the generation and the load. Okay, so in this case, you have a minimization problem, so you are searching for a point here. So it is a convex problem. It's a convex. Okay.
Because of the bound that we are restricting to.
Assuming what?
Because of the boundaries that we are restricted to. So we can say it's convex in this case.
Yeah, of course, طبعا, as I mentioned, if you have this function over this range, you cannot say this function is convex or concave. In this range only, you can say this is concave. In this range, you can say the function is convex. If you take the whole range, you have boundaries. Definitely, you have boundaries. This is the search space, and you have to define the limits of the variables. And in this case, you can see whether the function is convex or concave over this range.
Okay, clear now. Thanks, folks.
Okay. So this is the function. What about the region? What is a convex region and what is the non-convex region? The definition of the convex region, if you arbitrarily choose any 2 points, in this region, the straight line between these 2 points or the interpolation of these 2 points completely inside this region. If any interpolation of these points or the straight line completely inside the region, but this is the convex region. Assume that you need the point here and the point here. So the line between these 2 points completely inside this. You have a point here and a point here. So all these lines are inside. If you choose any 2 points arbitrarily, the complete line in between will be inside the region. So in this case, we call it convex region. This is non-convex region. While if we choose any 2 points inside the region, the straight line in between or the interpolation between these 2 points, the line is not completely inside the region. So in this case, this is a non-convex region. This is a non-convex region. Okay. So this is the convex region. Any interpolation between any 2 arbitrary points, the line is completely inside the region. And for this one, the line is not completely inside the region. So this is non-convex. This type of problems, if you have the search space as such, is non-convex. Such search space creates a problem to classical techniques of optimization. إنما for يعني حكاية الconvexity as a condition for classical technique is not there for evolutionary computation. Whatever, you can end up with the good solutions in whatever the region is, whether convex or non-convex. With the evolutionary computation, you can handle this efficiently. But this is a condition for the classical technique. So this needs you to be aware about the search space in advance. And such limitation is not there in evolutionary computation. A convex set of points exists if for any 2 points, xa and xp, in a region, all points or interpolation between xa and xp, mu or theta or whatever, this is a dummy variable between 0 and 1. So all interpolation inside the region. And the straight line joining xa and xp are in the set. This is the condition for the convex region. Is it clear? Okay. طيب, sometimes you have problems, you need to minimize sometimes you need to maximize, for example, minimize the cost, minimize the losses, maximize the profit, maximize the quality. So can we change between minimization and maximization? No, definitely if you have a code, or if you develop a code or whatever, in this case, the code is designed, for example, for minimization problem. Can you still use this code for maximization? Okay, if you develop a code for minimization problem, and you need to implement to take this code also and solve a maximization problem. Can you do this?
Yes.
Salem?
Yeah, it's the inverse of each other.
Inverse of each other, exactly. This is the case. Very simple. You can have this maximization problem. This is the maximization problem. You need to search for this value, X star, the optimal solution. This is the optimal solution here. If you multiply this function by minus sign, so this is the minus f of x now. So you need to, this X star represent in this case is the minimization problem. This is the minimum, or this is the global minima here. For the function, this is a global maximum. For the inverse of the function minus f, this is becomes the global minima. So you can still use the same code, but you multiply the objective function by minus sign. So if you have, for example, minimize f of x, so this is equivalent to maximize minus f of x. Is it clear?
Yes, it is clear.
Yes, doctor.
Okay. Great. So maximization f of x, it is equal to, you replace f of x by or minus f of x by g of x, and you maximize or minimize this one. So minimization and maximization problems are thus interchangeable. Depending on the problem, the optimum is either maximum or minimum. Later, after solving the problem, you can reverse again, multiply the objective or the function by minus sign to get the exact values. Type, what is the necessary condition and what is the sufficient condition for optimality? What is the necessary condition for optimal solution? What is the necessary condition? This is the necessary condition. And the sufficient condition for optimal, maximum, minimum, and so on, d square f by dx square. If it's greater than 0, less than 0, equal to 0. So these are the necessary and sufficient. Of course, we can expand this if you have several variables. So in this case, you have the gradient, partial f or partial x1, x2, x3, x4. So we have a vector here. And if this is also, this second derivative will be a Hessian matrix. So in this case, you have a Hessian matrix here. So this is the necessary condition for the optimality at x star derivative equal to 0. And if x equal to x maximum, so this is before and after. Of course, you have the derivative is different, positive and negative, but at the global or at the optimal solution, the derivative equal to 0. So this is the necessary condition for optimality. If this is the function, you can have a, b, c, d, all these points derivative equal to 0. Here you have a and d are A and B are maxima, B is minima, and C is what? Flat point, inflection point, saddle point. So this is the inflection point. يعني you have your positive and this is low. Derivative is equal to 0. Yes.
Just a question for the necessary condition for optimality. So we have two condition or one condition only? I can see what I understood from this, that if we get df by dx, that means we have the optimal solution. And when we have the...
This is necessary to have the optimal solution. But what what is the optimal solution? Are you going to maximize or minimize? Okay. At maximum and the minimum, derivative equal to 0.
Okay.
At maximum and the minimum, derivative equal to 0. Right? So this is a necessary condition. df by dx equal to 0. This is, I don't know why this this gives you the stationary point.
Yeah.
You may have maximum, you may have minimum, you may have inflection point here. In order to differentiate, in order to identify whether it is maximum or minimum or so, you have to go to the second derivative and check whether it is positive, whether it is negative, or equal to 0. In this case, you can say, no, this is minimum, maximum. So this is a necessary. So this is the necessary condition, and this is sufficient. I don't know what is very sensitive as such. Anyway, is it clear, Fawzan?
Yes, yes.
Okay. How can we distinguish between minima and maxima? By the second derivative. You go to the second derivative, and you can see second derivative less than 0, معناها maximum. So you have at point D and at point A, you will find the second derivative less than 0. And the objective function is concave around the maximum point, the concave, convex here, and here, this is the inflection point. So, yes, at point B, second derivative is greater than 0, so this is the minimum point. And at point C, the second derivative equal to 0. And this is inflection point. Okay? Now flat point. Now the function is flat around point C. Any question? I think these are very simple concepts. So the necessary condition and the sufficient condition for this. If you want to expand this for multivariable x1, x2, x3, in this case we have to go for the Hessian matrix and the gradient vector. For the first derivative, gradient vector, which is partial f by partial x1 up to partial f by partial xn. So, and these are the Hessian matrix, which is the square matrix n by n. And you can solve the necessary conditions to find the stationary points, and then you can get the eigenvalues of the Hessian matrix in order to differentiate between the minima and maxima. If all eigenvalues are greater or equal to 0, the matrix is positive semi-definite, semi لأنه equal. If it is not equal, in this case, it was strictly positive. So positive semi-definite, the stationary point is the minimum. If all the eigenvalues are less or equal to 0, the matrix is negative, semi-definite, and the stationary point is maximum. If some of eigenvalues are positive and the other are negative, we have the third case, which is the saddle point or flat point. So I think this addresses your question, Hussein. Are you still with us?
Yes.
So these are the all conditions for the eigenvalues. If they are greater than or equal 0, then at maximum, less than or equal 0, that's minimum. Okay, or minima. If it is greater than or equal 0, يبقى local minima, local maxima, and here you have the flat point. If some of them are positive and some of them are negative. Type, okay, so we have two types of optimization problems, which is constrained and unconstrained problem. Unconstrained problem, you have only the objective function, and you need to minimize the objective function as such. And there is no constraints on the variables. So in this case, it is quite easy. You can take the derivative equal to 0 and solve, and then you check the second derivative, and you can say, you know, this is positive, this is local minima or local maxima, or flat point. And this is straightforward. We have a question here from Hisham Muhammad.
Yes, doctor. Actually, I wanted to ask if the second derivative is a constant function, what can we say about
positive
this?
or negative؟ بغض النظر عن هو constant، هو positive or negative. لا هو طبعا هو لازم يبقى constant. ليه؟ لأنك أنت you solve here for this value of x. You get it from here. And then you substitute about on x here. Okay? So if you substitute here, in this case, you may have 2 or minus 2 or 0. So this is greater than 0, this is less than 0, and this is equal to 0. Is it
No,
clear?
actually, I meant the second derivative. If the second derivative doesn't have any variables, we get the constant.
It shouldn't have any variable. لأن الvariables أنت you substitute about x here. You get x from here and you substitute it here. But when you substitute by x, in this case you have a constant matrix here or constant value. أنت متخيل؟ يعني احنا لو أنت عندك مثلا f of x equal to x cube plus x square مثلا, for example. f prime equal to 3x plus 2x, 3x square. Am I right? F double prime equal to 6x plus 2. Am I right?
Yes.
Here we need to find the optimal point. So you equate it with this as 0 here. So this is, if you solve this equation, 3x squared plus 2x equal to 0, we have x 3x plus 2, so equal to 0, either x equal to 0 or x equal to, this is equal to 0, minus 2 over 3. You take this x and substitute it here. How much f double prime if x equal to 0? It is 2. Am I right?
Yes.
If x equal to minus 2 over 3, minus 2 over 3.
Minus 2.
How much double prime? It is minus 2. So this here, this the second derivative, you substitute by x what is given here. So at the end, you have a constant value. And this constant could be positive, could be negative. This is the local minima, and this is the local maxima. At this point, you have a local maxima, and at x equal to 0, you have a local minima. Is it clear? Yeah.
What about if our function is x square only? The second derivative will be 2.
طيب خلاص يبقى وده منطقي جدا لان اكس سكوير اهي ادي اكس سكوير مش دي الفانكشن اكس سكوير؟
Yes.
يبقى we have local minima only. يبقى f double prime will equal to 2. So it's greater than 0. So we have local minimum. Only one point, local minimum. Now, if you have different points here, and you have two stationary points, at this stationary point, you have a local minima. At this stationary point, you have a local maximum.
It's clear. Thank you, Doctor.
And also, if you go and constitute the Hessian matrix, the H matrix, again you have all these variables x1, x2, and so on, and you substitute here. At the end, you have this Hessian matrix as a constant matrix. So you can get the eigenvalues of this matrix. Okay?
Yes.
For a set of parameters, the gradient of f vanishes at a local extrema, whether minimum or maximum. To be a local minimum, the Hessian matrix must be a positive definite matrix, positive eigenvalues. And this is the Hessian matrix, as we mentioned earlier, and this any entry of the Hessian matrix. So let us take this example, very simple example, unconstrained optimization. There is no limitation, there is no limit boundaries. We don't have equality constraints or inequality constraints. And this is a straightforward problem. You have two variables here, x1 and x2. You can get partial c by partial x1. You can the derivative, this is equal to 0. Partial c by partial x2, this is equal to 0. So you have here two equations and two unknowns. So you can solve these two equations together, right? Is it clear? You can find x1 and x2. If these are nonlinear functions again, so you may need to get the Newton-Raphson method or Gauss-Seidel method to solve. So the solution of this definitely equal to 0 and 0. If you add them up, it becomes 6x2 equal to 0. So x2 equal to 0, substitute to get x1 equal to 0. So this is the stationary point that we have in this function. This is the only stationary point. Okay, let us take the second derivative. Partial square c by partial x1 square, partial square c by partial x1 x2, partial square c by partial x2 square, and so on. So we can form the Hessian matrix. This is the stationary point. We can form the Hessian matrix. This is the Hessian matrix. And here Hessian matrix is constant. Even we don't need to substitute about. This is the same case as you assume, Hisham, the conversor. So here is the constant matrix. So let us see. And actually here we have only 1 point. We have only 1 point. So we need to check this point, whether it is local minima or local max. So let us find the eigenvalues. Lambda I minus A equal to 0 derivative. You can get the determinant of this equal to 0, and you can solve for lambda here. So H must be positive definite, must be positive, and so on. And you can have lambda I minus A equal to 0, determinant of this. And you end up with this equation, lambda square minus 10 lambda plus 12 equal to 0. Can we solve this second order equations, lambda equal to minus b plus minus square root of b square minus 4ac over 2a. So you can easily find lambda. Here lambda is 10 plus, يبقى positive, 10 minus second square root of 50 is almost 7. So 10 minus 7, it's still positive. So the two eigenvalues are positive. وبالتالي this point, which is 0, 0, is local A. Here lambdas, lambda 1,
Local
lambda
minimum.
2 greater than 0. So what is the local minimum? Okay.
Doctor.
Yes. Fauzan?
Yes. The inequality.
I couldn't hear you well, yeah, Fauzan. Can you repeat?
No.
Can you repeat?
Yeah. Equal. What I now lambda can say that it's only greater 0 instead of saying greater than or equal.
Yes. Yes.
Yeah.
Lambda 1 is greater than 0, lambda 2 is greater than 0. The definition of local minima is lambdas is greater than or equal in general. Okay? If they are greater than 0, that's fine, no problem.
I'm trying to link it to either strictly.
Yeah, in this case, yes, this is strictly positive, definitely. Then all lambdas are greater than 0.
Okay.
So the stationary point is a minimum point. Again, this is another example. You have how many variables do we have? We have 3 variables, x1, x2, x3. And then you can, 3 equations here, x1, x2, x3. So you can, in principle, you can solve the 3 equations in 3 unknowns, and you can get x1, x2, x3, which gives you the, of course, these are linear functions. You can put them in matrix form, A, B, A, X equal to B. So this is A, and the coefficients of x1, x2, x3. Otherwise, it becomes 2, 1, x3 equal to 0, and this equal to 8. So you can put them in, or you can solve them, whatever. These are 3 equations, 3 unknowns. You can, by a way or another, you can solve them. So you can have this stationary point that we have. This point is 3, 2, 5. This is the stationary point of that function. So next step is to find whether this minimum or maximum. So we can go to the Hessian matrix, and this is the Hessian matrix. Okay, this is the Hessian matrix. You can take the derivative of these again, x1 square and x2 square and so on. But this is, you can have this Hessian matrix, and you can find lambda I minus A, determinant, or minus H. In this case, Hessian matrix equal to 0, and you can find lambda to see whether where is this is maximum or minimum. So you can find the eigenvalues of this matrix as 1.54 and 6.45. So all of them are positive, greater than 0. This is the minimum point. Okay? Is it clear? I think the examples are straightforward. Let us, as I mentioned you earlier, we need to be ready for a simple quiz. So I assume that you have your blackboard ready and open in order to, if you have here, I'll make it available now. So you can just take 3 minutes to solve this this quiz, this simple quiz. Okay.
Okay.
What is this? Did you see the quiz?
Not yet, doctor.
In which part, doctor?
The introductory part. The introductory part.
No. In the blackboard, in which part?
In the blackboard,
Assessment?
in the assessment and test.
Okay, good.
Assessment and test, you have quiz number 1. Did you see it?
Not yet there.
It's not there?
Not yet, we cannot see. Yeah, it's not there.
It's not there. Yeah. Are you sure يا شباب؟
Yes, doctor.
Yes, nothing is there.
شكله ياخذ وقت يا دكتور.
ليه هو يعني رايح يعني ماشي، هو جاي ماشي ولا ايه عندكم؟
لا يسوي تشيك الكورونا يا دكتور.
لا انا I think انه it should be available now.
Now.
Yep, it came now.
طيب take 3 minutes.
Okay, now it's there.
Okay, great.
How many questions is it there, doctor?
3 questions. 3 questions. That is just يعني some kind of
Doctor?
yes.
Can you actually see if we submit the quiz? Because it's still appearing on my side, even after I submit it.
If you submit it خلاص يبقى.
Doctor,
No.
can we go back if you want to check?
Go back to what?
Like question, I'm in question 3, I want to go back question 2.
You cannot.
Okay.
Cannot. Okay, I think let us go back to our class.
Doctor, if we are done, can we leave?
Yeah, we still have 2-3 minutes in the class.
Oh, sorry. I am sorry, doctor. I apologize.
And usually the quiz could be at any time in the class. Yani it is not necessarily to be at the end, or maybe at any time during the class we can have the quiz.
Actually, I asked because I thought the class ends at 9:20, so I will return again.
9:25.
Yeah, I realize it now. So sorry.
Okay, no problem. So solving now, let us solve a constrained optimization problem. If we have constrained optimization problem, if we have equality constraints or inequality constraints, in this case we will use what we call the Lagrange multipliers in order to convert the constrained problem to unconstrained problem. How to do this? The key idea is to modify the constrained minimization problem to be unconstrained problem. So the original optimization problem is minimize function subject to, these are the condition here or the constraints here, and G equal to 0. You have equality constraints somewhere here. So this is the constrained optimization problem. In order to convert it to unconstrained problem, let us expand the objective function. This is the original function, objective function. Let us create what we call the augmented objective function. This objective function, what you did here is you add another term here to the original objective function. This equal to the constrained multiplied by a constant here or parameter here equal to lambda. So you multiply the constraints by lambda. If you have 2 constraints, 3 constraints, each constraint will be multiplied by lambda 1, lambda 2, lambda 3.
You are on mute, doctor.
You keep, and I'm talking about 2 or 3 minutes now.
No, just
No, it was muted for a little bit, not too long.
Just the last half minute.
Okay. طيب, يعني here we converted the constraint problem here. This is objective function, this is the constraint. We add this constraint here. And you add this constraint here to the objective function plus lambda times g. If you have several lambda 1, g1, lambda 2 times, يعني if you have مثلا constraint x2 أو x1 plus 3x2 minus 6 equal to 0. This is the equality constraints. So you multiply this by lambda times x1 plus 3x2 minus x6 minus 6 here to the objective function. So you convert the constrained optimization to unconstrained optimization here. And you can, here you have x1, x2, x3, x4, and so on. Now you add another parameter here or another parameter here, lambda 1, lambda 2, lambda 3, lambda 4, and so on. So in this case, instead of having only 3 parameters, you expand this to include all these lambdas. And the same necessary condition is there. You have to get partial L by partial x1, partial L by partial lambda 1, partial L by partial lambda n. So you have here more variables, but the beauty here is you convert from constrained to unconstrained problem. So number of equality constraints, each constraint will be multiplied by lambda. Lambda is called Lagrange multiplier, and L is the augmented objective function. called Lagrangian. In recognition to Lagrange. Partial L by partial x is equal to 0, partial L by partial lambda is equal to 0. You solve this set of equations together and you find the solution. Implicitly, the condition or the constraint is satisfied. I know I took more than the time, but let me answer Salim, and then we can close the session. Salim, please.
Yeah, Professor, for the Lagrangian multipliers, are we talking about the binding constraints or all type of constraints available?
Now what we have here, yeah, definitely you will do the same for inequality constraints. But for this specific example, we started here with the equality constraint. For this equality constraint, you can add it here right away in this case, okay? You will do the same also for inequality, but we will talk about inequality later on. So let us move.
Okay.
Okay. So again, this is the necessary, and I think we can continue next class when time is over. So if you have any question, please stay and ask. Otherwise, you can leave now.
Just to start the solving constraint optimization.